Okay, so we are going to get as far as we can with the rest of Chapter 8. I think we got through about half of it last time. Yeah, okay. So really, and I apologize, I'm kind of going to hurry through some of this, but last time we talked a lot about the physics of wave technology. We discussed a little bit some of the technologies themselves. I'm realizing that I didn't quite get to the last figure or two of part one, so let me zip forward to that. Okay, I know we covered that. Oh, okay. I know we spent a little bit of time talking about stresses last time. We talked about forces, we talked about stresses. Another thing to keep in mind, in a two-dimensional system like we see on the screen here, there are three different ways something can move. It can move up and down, so they're calling that heave. It can move back and forth, they're calling that surge, and it can rotate. They're calling that pitch. So thinking back to 101, each one of those modes is a way to harness energy. They're mutually perpendicular, and you can see that little buoy can do one of them, the other one, a combination of two, a combination of all three, and each one of them is going to give you some energy if you have a generator attached to it. Very similar to the technologies I was talking about before with the roadway energy harvesting. You can have something sliding back and forth, moving up and down, spinning in a circle, what have you. Just something to think about in terms of energy harvesting. Okay, so here are several different various types of wave energy converters. Each one of them is using some combination of heaving, surging, rotation. Sometimes it's just water-based. You can also see get the tap chan that we discussed before. Some of them have a flexible bag, so you have air, just like in that water or air-water channel that we looked at last time. Okay, so that was it for that set. Okay. Yeah. Now we get into these guys. Okay. And this is just showing really different places where you could deploy your technology. We talked a little bit about the optimal place. So you're kind of going to want to use a natural feature if you can get it. If you get too far offshore, it gets expensive. If you're too close to shore, it could get beat up, unless you've got this neat little thing called the oyster there. You can see it's just sort of taking advantage of a rotational motion. So, most of these general strategies have been fairly well thought out. Okay. And again, these are just kind of cartoons showing how different modes through which energy can be harvested. The point absorber just says that it's got relatively small dimensions compared to the incident wavelength. So the wavelength itself is here. You've got pressure waves moving up and down. Remember last time we talked about the difference between pressure and stress. Pressure is the same in all directions. Stress is 9 or 6-dimensional, depending on how you think about it. The attenuator, it says principal axis to the wave front. Wave energy is gradually drawn in towards the device as the wave moves along it. I do have a colleague in Seattle. If you're interested in going into this type of technology, he owns a firm called Oscilla Power, OSCILLA, and they have attenuation technologies that they're deploying in the Pacific Ocean. The technology itself really does not have any moving parts. It's more or less a piezoelectric material. I shouldn't say no moving parts, just just very small vibrating parts. Well, big parts that vibrate a small distance, in a similar way to how a microphone or a speaker works in your car. So in a microphone, you speak, something vibrates, that mechanical vibration is then turned into electrical energy. So I in fact, know somebody quite well who's working on this exact technology. Okay. Here's a shot, wave tank. So a way to do testing of devices. So rather than go to the expense of running your tech all the way out in the ocean, just head over here to Edinburgh and run the wave tank. Make sure you're getting the data you want, and then you can deploy it out in the ocean. Similar like you'd see a wind tunnel. If you're going to build an airplane, you'd put in a wind tunnel first. Okay, this little shot here is always very intriguing to me. You look at that wind turbine there, and you're like, gosh, why is there a zero angle of attack on those little blades? Well, the reason is so that the turbine can run in either direction. The wind can blow from the front or from the back, and that's more or less what's happening as these waves come in and sort of slosh the air column back and forth into this chamber. So the next figure shows how that happens. So if you've got the airflow velocity is coming in here. So this is just the air coming into the system. If, or I should say when, the blade moves in this direction, and remember, think back to our wind chapter a little while ago. If you add this vector, so the air coming in, and this vector together, you get the hypotenuse of that triangle or the diagonal of that rectangle, however you want to think about it. That is the relative wind velocity. Now, I could also take this whole figure and flip it so that the bottom was on the top was on the bottom, and it's going to look exactly the same, only in reverse. So up and down really do not matter in this figure at all. The important thing to keep in mind is that the drag force is always, by definition, parallel to the relative flow velocity, and the lift is always, by definition, perpendicular to the drag. So you can see when you add your vectors together, there goes the drag. The lift is actually pointing forward, and it's the lift that makes the whole thing rotate. So that's how it works. You could flip it upside down and it would still work just fine. So you might look at this thing at first glance and go, it's never going to work, never going to turn. But do your physics. There it is. Watch it. Watch it spin, and here comes your electricity. Okay. So here's an example of how something like this might work. The butterfly valve is either going to be open as it is now to let the air go through, or closed in order to build up pressure. So you could imagine building up a big head of pressure and then let it blast open. But the point is, as the water comes in and out, the air column itself is pressurized, depressurized, back and forth. The turbine spins, and you make electricity. And here's just another shot of that. Okay. You've all heard of a rectifier in an electric circuit that turns an AC signal into a DC signal. Same basic principle here. This is just a mechanical rectifier that is turning the oscillating water chamber and the waves coming in into a constant output. Okay. here's one of your oscillating devices. So big pistons. You're going to have a back EMF down in this guy. So as the waves come in, it's sort of sloshing back and forth. That's basically like that little oyster we saw, close to the shoreline before. Again, another actuator where they're just using the heave of the water. Another thing to keep in mind is that in general, even though the waves are passing through here, the water itself is more or less just going up and down. These valves are a lot like those same valves from 101 with the miner's friend. Remember that boiler way back when? And there was, the valves would only allow water to flow in one direction, not the other. So you could think of this as a rectifier as well, and the water can only flow in one direction even though these pistons are going up and down. Several of them in series. There's one that's actually deployed. Here's one that's just floating. So taking advantage of the water flowing in, these pressure waves in and out, depending on what exactly is going on with the waves, tethered to the bottom. This would be, grid tied, for example, or it could just be running a buoy. So Tim Chester said he's, worked on similar technologies where you just need a light sitting out there in the middle of the ocean for safety reasons and steering. Not as big a deal with GPS now, but still. So here's an example, one that's been deployed. I don't know, but I would assume that these wind turbines are also collecting a little bit of energy for electricity to run the station. And the rest of these are sort of larger technologies, and I think if you remember earlier in the chapter, the authors were saying how there was, when the oil shock, the oil energy price shocks of the 70s were a big deal. These were much more economically favorable. We just did the same kind of argument with our beetle kill project, where how do you compete with coal? Well, you have to have some other product so that it becomes economically competitive and not just environmentally sound. Another floating technology. There's one that's just rotating. This is another pretty cool one too. I have seen much larger versions of this to try to kill hurricanes. So imagine something like this sitting out in the middle of the ocean that is sort of capturing small waves as they build up, and you sort of never get that big wave. And so rather than having the giant hurricane waves come sloshing into New Orleans, come sloshing into New York City, you pop one of these guys out in the ocean, waves come in over the edge, and then as the water flows out, you harvest the energy through a generator. So this is kind of a small one, but there have been proposals to much larger systems. So you're not only harvesting energy, but you're mitigating potential storm damage. This is another one, kind of a barrier. This guy just works by rotating back and forth. This one you can actually pilot around, go where the waves are. Okay. Well, I just want to wrap that up. There's a little deal on what this looks like with the grid tie. So you might have your diesel generator as a backup. Much bigger grid scale. So there's obviously been some good engineering done on this, and then. What they're also showing is that the nice thing about the wave tech, unlike some of the other technologies, is that it tends to follow the seasons. So in January and February, when you've got your most weather out there in the ocean and you need your lights on in the dark, if you've got electric heating, you need that, it follows. I don't think they're probably talking about a northern climate because June and July and August. If this were a hotter climate, you'd see air conditioners coming on in the summer, but there you go. Okay, well, thanks for this afternoon, and we'll see you on Tuesday.